Okay, everyone, I'm back. Just want to say for the record, in case someone's watching the recording later, that I had some internet connection problems, which caused us to end our lecture prematurely. Hopefully, there'll be no more of that nonsense. The recording will probably have to be in 2 parts now because of that. But I'm recording again, and we're going to continue by learning about how photons are produced by studying something called the 3-to-2 transition of hydrogen. If we want to figure out the energy of the photon, we need to figure out the energy lost when the electron drops from orbit 3 to orbit 2. And just before we had lost connection, I asked, I don't know if it was Dennis or somebody had taken a peek at my my energy level diagram, and they got 12.1 minus 10.2 electron volts. And you guys can see that that's equal to 1.9 electron volts. Although for today's answer, I need a little bit more precision. So I'm going to give it 1.894. I added the extra sig fig manually. Sorry about that. And this energy is going to be the energy of the photon that's released. We have a goal here. We want to learn about this photon. What is the nature of this emission line? Why don't we find the wavelength and find out what regime of the EM spectrum this photon is located. So we learned some basic formulas in our office hours today. We also learned some formulas in our lecture, in part 1 of our lecture. Which formula would be the best formula to choose if we want to take the energy of a photon and convert it into a wavelength? What do you guys think?
So is that out of the 2 formulas we used today or something like that?
Yeah, there were 3 actually.
3?
I ended up.
All right, yeah. Let me just.
Well, I better push this along. Dennis, I was hoping you would say the 3rd formula. The energy of a photon is Planck's constant times the frequency over the wavelength of light. Here we're going to want to rearrange the equation and solve for wavelength as h times c over E. First, let's convert the energy to joules. If I start off by writing 1.894 electron volts, what's the conversion to joules? Could someone look that up in the notes? I gave it to you under wavelength, frequency, and energy. Tess, can you tell me what it is? Megan? Just look it up. Michaela, someone help
Did you
me.
say the units for did you say the units for joules?
Well, that doesn't make sense.
No, I'm sorry. What? Can you repeat the question? Because I'm apart in my notes. So
I'm
sorry.
trying to convert the energy from electron volts to joules.
All right.
I need to convert
It's
Anyone's call. I'm just looking it up.
1.6 times 10 to the negative 19
Where
joule.
does that go? Top or bottom?
Top. And then 1 on the bottom.
Okay, let's keep 4 sig figs. What do you get? I'm going to go back up here. Four sig figs.
I got 3.0304 times 10 to the negative 19.
All right, we'll keep 3 sig figs. All right. Now we're going to plug that into our formula. Wavelength is equal to Planck's constant. Oh, guys, do any of you watch the show Stranger Things? It's kind of a cool, like, homage to Spielberg 80s movies, and there are some kids that discover a 4th dimension upside down world, and there's a monster. It's kind of cool. It's on Netflix. If you haven't seen Stranger Things, I'd recommend watching it. It's pretty fun. There's a plot point where one of the characters has to like unlock a safe, and it requires them to know Planck's constant to like 6 digits of precision. Now, the real value of Planck's constant, if we look it up here, it's 6.6260704. I just rounded all this bullshit to 7 for most of our exercises because I don't care. But today I'm going to keep 3 sig figs, 6.63, because I'm trying to do a slightly more advanced, more detailed, more precise calculation than usual. So today for Planck's constant, we'll have 6.63 times 10 to the minus 34 joule seconds. That's going to be multiplied by the speed of light, 3.00 times 10 to the 8 meters per second. And we'll divide it by the energy of the photon, 3.03 times 10 to the minus 19 joules. Why don't you guys punch that in for me? Do it quickly because we have a lot to cover before the end of class today.
I got 6.53 times 10 to the negative 7.
6.53?
Yeah?
Oh, wow.
Can't we just round up to 7?
I did not get 6.53.
Oh, that's weird. Let me try it again.
I got 6.56 times 10 to the minus 7.
You can't hear me because I was muted. I got 6.5 also.
3 sig figs this time. What was your third digit?
6.
Good. What are the units?
Meters.
What is it in nanometers?
Will that just be times 1,000? Right?
No, it's a billionth of a meter to 1 nanometer. It's times a billion.
Oh. So that'd be times. So.
Megan, did you fix your mistake?
Yes.
How many nanometers?
That can't be right. 656?
That is right.
Wow. I mean, no, of course that's right. That's what I meant to say.
In what regime of the electromagnetic spectrum is a 656 nanometer photon found?
Ah, look at this.
In what regime of the electromagnetic spectrum would I find a 656 nanometer photon?
Your?
Huh?
Oh, hold on.
VIBGYOR, which is what?
Visible.
The visible spectrum. And now let's go to a more advanced picture here. What color would that correspond to? 656.
Red?
Yeah, it's a deep, deep red. So let's write that down. In fact, write down underneath that, it's in the visible spectrum, and this photon has a brilliant red color. This is one of the most famous photons in the entire electromagnetic spectrum. Astronomers know it as hydrogen alpha. It's actually a red line at exactly 656.3 nanometers. And as an example of where you might find it in space, let's take a trip out to the Rosette Nebula. The Rosette Nebula is a massive cloud of hydrogen gas that is surrounding some newborn bright blue stars. These stars produce tremendous amounts of ultraviolet light, which is capable of heating up and ionizing hydrogen gas. When the hydrogen gas starts to cool down, shit, I want the big picture. Give me this little picture shit. Yeah, there you go. Look at that. Look how dope that is. All of this hydrogen gas is producing a brilliant red light at exactly 1 wavelength, 656 nanometers. And it's all being caused by electrons which are dropping from orbit 3 to orbit 2 in the hydrogen atoms. This cluster of bright blue stars is pumping out lots and lots of ultraviolet light, which heats up the atoms and makes their electrons jump up to the 3rd orbit. And then when they cascade and drop back down, they transition from orbit 3 to orbit 2, and they're all simultaneously emitting exactly the same color of light, 656.3 nanometers. They call this an emission nebula, but really it's like a laser nebula because the entire nebula is being powered by one hyperspecific super red wavelength of light. Also means that what's happening in the microscopic world of atoms is what's creating this beautiful red cloud of gas that we see in space. There are also other photons that hydrogen can produce besides hydrogen alpha. Let's take a look at some of them. According to this, you can see, let me get an annotate here. A drop from 3 to 2 produces a photon at 656 nanometers. What transition is responsible for the blue photon, which is at 486 nanometers? This is called hydrogen beta sometimes. This is hydrogen alpha. What transition causes the hydrogen beta photon? Can you look up here and tell me? Does anyone understand my question?
Did you say what level causes the hydrogen beta?
All photons are produced when electrons drop from a high orbit to a low orbit.
Mhm.
And there are all these different transitions that can happen. The energy levels or the orbits are usually represented by some kind of an energy level diagram. I was hoping that you'd look at the energy level diagram and tell me which transition, like for instance, the red photon is produced by the 3 to 2 transition of hydrogen. Which
Oh, that's the 4 to 2 for that one.
4 to 2 transition. That's
Yeah.
when an electron drops from orbit 4 to orbit 2. What about the so-called hydrogen gamma photon? That's at 434 nanometers. What transition causes that?
5 to 2.
5 to 2. Very good.
And then what would be the ultraviolet? Because I don't see it up there.
Well, the ultraviolet isn't listed here, but you can see that there clearly are transitions which produce ultraviolet photons. All of the transitions that drop to orbit 1, these are all ultraviolet photons. And by the way, after the electron drops from orbit 3 to orbit 2, it usually then proceeds to drop to orbit 2 to 1. So actually, if we look at the Rosette Nebula in the UV, I'm still recording, right?
Yeah.
You can usually see the 2 to 1 transition. And we can actually look at the Rosette Nebula at different wavelengths of light to see different types of atomic physics at work. This is what the Rosette Nebula looks like in the ultraviolet. You'll notice the stars don't look quite the same, but you can see the hydrogen gas there is emitting 2 to 1 transition. Okay, so what have we learned? We've learned that hydrogen produces a kind of unique spectrum of light. It does not produce a rainbow, but it produces 3 unique lines in the visible. What color do you think glowing hydrogen gas would look like? What would you get if you combined red, blue, and purple together? What color would that be? Who knows their color mixing?
I think it would be purple.
Say that?
Purple.
Yeah, because red and blue makes purple, right? I actually have a hydrogen gas tube. It's a little contaminated by air, but if you guys look here, this is going to be what our lab is about today. This tube is full of hydrogen gas. And I'm going to sort of put it into a power supply.
I think I've done this with the chemistry class one time.
Yeah, it's classic.
Yeah.
Each atom produces its own set of emission lines. So I just put that into a power supply. Let's see if I can get some juice right here. See that? Look at that deep electric color. That cool electric purple is not just any old purple. It's being made by 3 lines together. Now, usually what happens in spectroscopy, the science of breaking apart light into its component wavelengths, the scientist will either use a prism or sometimes they'll use a tool called a spectroscope. And the spectroscope has a little piece of plastic in here called a diffraction grating, which will split light apart into its component wavelengths. And so what you do is you send the light into this tube. It goes through a slit. It bounces off the grating, and then it disperses into its component wavelengths. And that's what we're going to do in lab today. We're going to look at the spectrum of a bunch of different elements. So let's draw out the spectrum of hydrogen. And let's do that over here on the board. Sorry. So what we were just talking about is known as the hydrogen emission line spectrum. A spectrum is what you get when you break light into its component colors. And for hydrogen, it consists of a red line at 656 nanometers. Sometimes astronomers refer to it as hydrogen alpha. A blue line at 486 nanometers. That's known as hydrogen beta. And a purple line at 434 nanometers. That's called hydrogen gamma. Taken together, these three lines are known as the hydrogen emission line spectrum. And each atom is going to produce its own unique emission line spectrum. Each atom produces a unique emission line spectrum that helps you identify that atom when you break light apart into its component wavelengths. Sometimes people refer to it as a chemical fingerprint, but in light. Let me show you a couple of examples. Sorry. So I have a few function F5. So many buttons to hit. Function F5, 63. Somewhere around here you can see a bunch. Now these are all plotted backwards so that red is on the right. This is Roy G. Biv instead of Bib G. Yor. Here's hydrogen, one red, one blue, one purple. You can see sodium is famous for having the double yellow emission line in the visible spectrum. So sodium only has one emission line in the visible domain, and that's the yellow doublet. You might have actually seen this if you've ever been cooking ramen noodles or salty pasta water. When the salty water spills over the edge of the pot and hits the flame, it makes a little burst of yellow. That little burst of yellow you're seeing is the sodium doublet. Notice that helium has a different spectrum. It's got a red line, a yellow line, a couple of teals, and a couple of blues. Neon has a ton of red emission lines. We'll look at this. Mercury has a double yellow, a green, another green, and a few blues and violets. Every single atom in the periodic table sort of has its own emission line spectrum. Here's a cool picture that I found. It's the periodic table of the elements, but instead of showing you the elements, it shows you the unique emission line spectrum of every single atom. And you can see that no two atoms are exactly the same. Thank God for this. This allows us to do the art of spectroscopy. This allows us to analyze light and look for these emission lines, and that's how we know what elements the stars are made out of.
Why is there some of them with none?
It's not that there's none, Brandon. It's that these are all shown coded by intensity. So what's happening is these lamps are much, much brighter than hydrogen. Do you see how hydrogen is really, really faint here?
Yeah.
It's just relative intensity. So whoever did this photograph, if they had done a better job, what they should have done is they should have normalized the intensities so that these lamps were they probably took the same photo with the same camera each time, right?
Yeah.
But since these lamps were much brighter, by contrast, these are much dimmer. They should have normalized all of the intensities if they wanted to do it right. So it's not that there's none, it's just that they're too faint to see on the screen there. Okay, so what does this mean? Well, it means that there's different types of spectra that are produced in nature. Sometimes we get emission line spectra. It's also possible to see these types of spectra in absorption. And let me show you what an absorption line spectrum is. An absorption line spectrum is when you get a complete rainbow, but the individual lines, which correspond to the same emission lines, are removed from the spectrum. Absorption happens when an electron sits at the ground state of the atom. It's in a low energy orbit. And a photon of just the right wavelength comes in, and the electron grabs the photon and uses it to jump from low to high orbit. When that happens, the photon gets removed from the spectrum of light, and you see a black absorption line in its place. The person who tried to explain to us what types of spectra we find in nature was a Prussian scientist named Gustav Kirchhoff. And he came up with a set of laws of radiation to describe the 3 different types of spectra that we see in nature. There are continuous spectra, which are basically like a rainbow. Sometimes light produces an emission line spectrum, and sometimes light produces an absorption line spectrum. Let's take some notes on what are called Kirchhoff's 3 laws of radiation. They're intimately related to the art of spectroscopy. This is called Kirchhoff's 3 laws of radiation. And it attempts to teach us how the different types of spectra are produced in nature. The first law is known as the law of black bodies. Black bodies is a term used by old-fashioned scientists to describe hot, dense objects that glow because of temperature. So a black body spectrum is basically the same as a rainbow. And these are caused by hot, dense objects. I glow because I'm hot. Black bodies are things like filaments in light bulbs or pieces of metal in a furnace that are glowing. Coals in a fire could be considered black bodies. And the law goes like this. A hot, dense, solid produces a continuous spectrum. Whereas a continuous spectrum is code word for rainbow or white light. A continuous spectrum is usually white light. The second law is called the law of emission. This is going to teach us how emission line spectra are produced. A hot, thin gas produces an emission line spectrum, which we just saw in the hydrogen tube. And the third law, which I'll show you an example of in lab today, is called the law of absorption. The law of absorption says a cold, thin gas that is placed in front of a black body produces an absorption line spectrum. These are really key laws in understanding radiation. Sorry, underline absorption too. Hey, do you guys know what lecture number this is? Today we did homework 5.
I'm pretty sure it's 6.
1, 2, 3, 4. Wait, are you including the exam?
No.
No, this is lecture 7.
Okay.
Wait, which lab is it today?
6.
Oh, really? Maybe you're right and I'm wrong.
I think it's 7 too. Because I like write them down every time we start class and I lecture number 7.
Okay, that's helpful to me. Oh, did we not do a lab? No, we always do a lab, right?
We didn't do one last week before the exam because we just talked about the exam.
Oh, I was a little behind. So this would be lecture 7, but lab 6, right?
Yes.
Okay, I'm just trying to document this as I go here. This is part 1. It just finished the earlier video. Okay, let's take a look at this in cartoon form together. This picture here tries to show you all 3 types of spectra. A light bulb contains a filament. A filament is a hot, dense piece of metal. When it's heated up, it produces a rainbow. If I take hydrogen gas in one of those tubes and heat it up, I'll produce an emission line spectrum. But if instead I shine white light through the cloud, atoms will absorb those same unique wavelengths and produce an absorption line spectrum. All light falls under one of these 3 categories. Take a beam of light, break it apart, and it'll produce one of these 3 types of spectra. Here's a hint. Which one do you think the sun produces? If you had to take a guess.
Both.
What do you mean by both?
It does emission lines and spectra and the continuous spectrum
What about absorption?
and absorption.
You're actually kind of right. It does do all 3. That's very good. But if you had to pick one of them, I would choose an absorption line spectrum. Let me show you a picture of the solar spectrum taken from the Boston University Solar Telescope. It's pretty awesome looking. This is what the spectrum of the sun looks like, and it's actually kind of similar to the spectra of other stars. When you pass the white light of the sun through a prism, you discover what Joseph Fraunhofer discovered, the Fraunhofer absorption line spectrum, and that the sunlight is just pockmarked all the way through by thousands upon thousands of deep absorption lines. This is telling us about the atoms that are inside the sun. This is not one type of atom's absorption line spectrum, but it's the fact that there are all these different atoms in the atmosphere of the sun that are all absorbing different absorption lines. And basically, astronomers map out each one of these. Let me just get the solar spectrum as an image for you here. And astronomers carefully map out each one of these absorption lines to try to understand which elements are in the sun. For instance, here you can see the C line is hydrogen alpha, 656 nanometers. The D line in the sun is a yellow line in the middle of a double yellow line. Do you guys know what atom that corresponds to? We looked at it a minute ago. Which atom makes this double yellow line?
Wasn't it sodium?
Very good. That's the sodium doublet. And each of these lines correspond to different atoms as well. Here you can see them mapping them out. Oxygen, hydrogen, sodium, iron, you name it, it's in there. Okay. One of the last things that I'd like to do is focus on the law of black bodies. Hold on a second. Hey, Jordan, would you mind opening up a window just to keep it getting too smoky in here? It's kind of intense. So let's see. I want to talk to you guys about rainbows and about black bodies. A black body is something that's dense and hot, and it glows because of its temperature. I think if you tried to imagine a steel ingot in a forge, that would probably be the perfect conception of what a hot, dense solid is like. Let me see if I can find a cute picture here. There's one picture that I like more than others. Come on. My internet is kind of, well, maybe it's also because I have 10,000 tabs open. That's probably why. Don't need this. Might need that, might need that. Don't need that. Don't need that. Don't need that. Don't need that, but I like it. Might need this. Don't need that. Okay, here. When I think of a black body, this picture is kind of like the perfect picture. It's just a piece of metal which has been put into a furnace, and it's heated up until it's begun to glow. And the original scientists who were studying these types of objects wanted to understand what is the relationship between temperature and the amount of light that an object gives off. So they tried to measure for different objects of different types, as you heat them up, how much light will they give off and what types of colors will they give off. And they ended up determining a graph that looks a little something like this. It's called a Blackbody Spectrum profile, and I kind of want to walk you through it and talk about what it means. Sorry, I've got a slow response. Here's a perfect cartoon example of a black body. You've got an iron poker, you put it into a fire, and what do you see happening? At first it's cold and it does not glow. As you heat it up, it begins to glow, first a dull orange, then red, and eventually white hot. And although that's about as hot as you can make it inside of a fireplace, if you put that iron poker into a blast furnace and got it warmer and warmer and warmer, eventually the metal would glow a kind of creepy pale blue. And when the scientists made plots of the amount of radiation as a function of wavelength, they discovered that dense objects did not behave like gases of hydrogen or helium. They didn't all put out a unique emission line spectrum, but that as long as the object was sufficiently dense and solid, it wouldn't really matter if it was a lump of coal or a lump of steel or a lump of iron. They would all give off light in the same way. And let's look at what would happen for something that was about as hot as the sun, say 6,000 Kelvin. You can see here from the diagram that the x-axis is the quantity of, sorry, the y-axis is the quantity of light, and the x-axis is the wavelength in nanometers, in microns, with the visible spectrum shown here. And you can see that the sun is putting out light at all these different wavelengths of the electromagnetic spectrum, but that the peak amount of wavelength is somewhere in the middle of the yellow portion of the spectrum. But the sun also gives off some infrared, shown over here. This is infrared. It probably gives off some radio waves further down here. Also, it gives off some ultraviolet. and some X-rays, and some gamma rays too. So this is the entire electromagnetic spectrum. Let's focus on black bodies and let's talk about them. We're going to need these formulas for our next homework. So a black body is a hot, dense, glowing thingy. Okay? I say thingy because it's not always solid that produces black body light. The idea is I glow because I'm hot due to temperature alone. And black bodies usually produce some type of sort of white light or a rainbow. And that means they sort of contain all the colors of the rainbow. As I heat a black body, I get two effects, which can be described by two different formulas. And I'm going to cartoonify them so that you can sort of better understand them. The first effect is that more temperature equals more light. And this is expressed by a formula known as the Stefan-Boltzmann Law. The Stefan-Boltzmann Law tells me that if I have a lump of iron and I make it, say, 1 square meter, and I want to know how much radiation it's giving off, that the brightness in watts per meter squared is a number called the Stefan-Boltzmann Constant. This is the Greek letter sigma, kind of looks like an O with a baseball cap, and times temperature to the 4th power, where I've introduced the Stefan-Boltzmann constant of nature. Sigma is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th. The real aspect of this formula is to notice that the amount of light that I give off is proportional to the 4th power of the temperature. So very, very small changes in temperature lead to huge jumps in the amount of light that you give off. The second effect is that more temperature tends to produce what I am going to call bluer light. The light goes from red to white to blue. And this is expressed by a formula called Wien's law, I before E. Wien's law, which tells me that the peak wavelength of emission, lambda max, is 3 million nanometer kelvins divided by the temperature. That's kind of a lot, so let's get all that down. All right, before we end class today, I'd like us to try a sample problem where we kind of practice using these formulas. And I think the sample problem that we're going to choose will be, let's just imagine a sort of light bulb here. The filament inside of this light bulb is usually made of a metal called tungsten, and it's heated to a berserkly high temperature of 3,500 Kelvin. Let's try to analyze the light that's coming off of this tungsten filament. Does everyone have these notes? Because I'm about to erase. Okay. Let's draw our light bulb and our tungsten filament, and it's giving off some radiation, some light. A light bulb has a 3,500 Kelvin tungsten filament. Based on those givens, what I would like to do is, one, find the quantity of light emitted, and two, find the peak wavelength of emitted light. Which formula do I want to solve question 1? Which formula should I choose for question 1?
Be the first one, the one we did on the left, the
Stefan-Boltzmann Law.
Stefan-Boltzmann Law.
Okay. And what's that say, Dennis?
B equals sigma times temperature
To the 4th power.
to the 4th power.
All right. So let's put in our Stefan-Boltzmann constant. 6 times 10 to the minus 8. And that's watts per meter squared per Kelvin to the 4th. And that's going to be times 3,500 Kelvin raised to the 4th power. I'm probably going to have to show you how to do that. Okay.
Right.
Sorry?
I said I was writing it down. I didn't know if you wanted the class to do it or if you wanted me to do it.
Anyone. That's fine.
Yeah.
You guys want to see how to do this? Because you have to know how to put in your 4th power. So do 6 exp minus 8 times, just do 3,500. This button here is the raised to the power of key. So x to the y, we will raise that to the power of 4 and then hit equals. That's what you should see. Did everyone get that? Okay, what's my answer?
Nine to the power of 6. 10 to the power of 6.
So 9 million watts per square meter, right?
Yeah.
Brendan, does that sound like a lot to you? Considering that the luminosity of the bulb might be like 100 watts?
Yes.
So how am I supposed to understand that? How can that tungsten filament be producing 9 million watts per meter squared, but the luminosity of the bulb is only 100 watts?
Is that its maxed out point, like at the highest?
It's about the units, watts per meter squared versus 100 watts. What do you think? So for instance, here's a square meter, Brandon, right?
Mm-hmm.
I can't.
Is that, would that technically be the area it can cover?
Well, what this means is if I had a tungsten filament, if I had a sheet of tungsten that was 1 square meter, and I heated up that entire sheet to 3,500 Kelvin, then it would give off a luminosity of 9 million watts. But your tungsten filament, it's not a square meter worth of metal, right? Like if you took that filament and tried to hammer it into a sheet, I don't even think you'd make like a square millimeter or a square centimeter.
Yeah, isn't tungsten really heavy?
Yeah, you probably wouldn't be able to hold a sheet of tungsten. That's a separate issue, but tungsten is very heavy, very dense metal. One of the reasons they use tungsten is because I think it has the highest melting point of any metal in the periodic table. So normally if you took a piece of, I don't know, copper or something and tried to heat it up to 3,500 Kelvin, it would just melt.
I think I was looking, you can buy one on Amazon. It's a 4x4 for it's $1,000 and it weighs 41 pounds or something like that.
It was tungsten?
Yeah.
Holy shit. That's amazing. 41 pounds?
Yeah, for like it's literally like as big. It's kind of ridiculous.
I bet it was expensive as all effing hell too, huh?
Yeah.
Okay, cool. Let's try to answer the second question, then we'll get to our lab. Let's find the peak wavelength emitted. What formula do I want for that, Dennis?
You're gonna want Wien's law.
It looks like Wien's law, but Germans pronounce it Wien's law.
Wien's law. Yeah, it's my handwriting. Wien's law. Which is gonna be the max is 3 × 10⁶.
And that's nanometers times Kelvin.
Yeah, nanometers times Kelvin over T.
Over our temperature. Good. Okay. And our temperature here is 3,500 Kelvin. So what does that give us? You guys might actually, well, all right, just plug it in.
$857.
Let's call it 860. What are the units?
Nanometers.
What regime of the electromagnetic spectrum is 860 nanometer light found?
Oh, let me refer to the notes.
Uh-huh.
That'd be IR.
Yeah. Tungsten filaments actually, they peak just past the visible in the infrared.
So does that mean you could technically turn off or interfere with certain IR TVs and remotes and stuff?
No, because infrared is a huge band. There's the near infrared and the far infrared. Those remotes usually work in the far infrared, and this is in the near infrared.
Okay.
I guess if your source was bright enough. See, because a black body actually produces all kinds of different wavelengths. So if it's bright enough, maybe it could. If you look at the plot, you just calculated only the peak wavelength, which happens to be just past red into the infrared. But you'll notice it gives off light at a variety of different wavelengths. It also gives off visible light too. A tungsten filament usually produces more red light than it does violet light. And tungsten filaments have kind of a rosy glow that tends to make your face look nice, because red wavelengths of light are more flattering than green or purple ones. However, they are hideous wastes of energy. If your bulb is 100 watts, most of that power is going into just heating up the air around the light bulb. This is why an LED bulb can have the equivalent light output of a 100-watt light bulb, but LEDs only have to be 35 watts because they're not powered by blackbody light. They're powered by emission. They get emission lines in the green, in the red, and the blue to all mix together to make an artificial white light. And therefore, their energy is all being pumped directly into the visible domain. In other words, yeah, your bulb might have a power of 100 watts, but normally only 30 or 40 of those watts are actually making their way into the visible part of the spectrum. The other 60 watts are going into the infrared, which is just a total waste of your money and of energy and the environment. So LED bulbs are kind of cool in that respect. Okay, that's all we have time for today. It's now officially time for lab. And for our lab, we are going to do the spectroscopy lab. So does everyone have a copy of this sheet here?
I can go get one real quick.
Yeah, why don't you do that?
All right, I'll be right back.
Slide the computer over to the lab station. Actually, I need to print it out too. Oh, I was gonna close the window and turn it down to 72, just because I'm getting a little sweaty now. Sorry, I'm being high maintenance. Okay. Let me see if I can hit print on this bad boy.
So I won't be. My printer ran out of ink and I didn't realize. So I'm gonna try to figure something out with it.
So Brandon, here's some options. Do you have like a Microsoft Paint or like a paint program where you could put the colored lines in digitally and then resubmit it?
Yeah, I should have that. Let's see. Paint. Yeah, I got Paint.
Why don't you see if you can open that up in Paint, and then I'll have you put the lines in just kind of awkwardly in the digital domain.
Might not open because it's a PDF.
I got a printout of mine here.
See if I can figure this out. Open with.
Guys, I found this the other day. I've got check this out. I've got this lovely set of paints and pencils. I couldn't find this the first couple of times I did this lab, but look, I found this thing in the closet. It's been hiding there for years. And it's got all these markers. This is some gourmet shit right here. I've got all these beautiful colored pencils underneath. You don't have to have a set this nice, but I'm kind of psyched about it. Looks like I got a whole Roy G. Biv spectrum, right? Ooh. I got oils, I got watercolors. I'm gonna get, trying to pop these out here. Red, I'm gonna get green, violet, red, blue, purple.
So you can write. I don't know if anyone uses. I never use it because I'm always on Chrome. But on Microsoft Edge, apparently, if you open the PDF in there, they give you like there's like a little pen where you can change the colors and stuff and write on it and save it with all the writing on it.
That's very helpful info, Brendan. I wish I had known that in my previous classes because students were struggling to figure out how to do this. So what is Microsoft Edge again?
It's like the Internet Explorer that comes on the
Yeah, it's just Internet Explorer. It's just a
Yeah, basically.
a
'Cause
new
that's
name.
what I've been doing for all of my past labs, is that's how I've done it.
Oh, really? Wait, can you, just so I can share this with students in the future who are not as savvy as you guys, how do I never use Internet Explorer because I consider it to be basically fucking spyware, but
Oh
okay.
no, yeah.
So-
Can I share screens? I think I can, right?
You can if I give you permission, but some of my students used to share their screen. I don't know how to give you permission. I'd be happy to do it. That would be,
Or it said hold, sorry, I didn't mean to say hold. My bad. Host disabled participant screen sharing.
but I did no such thing, nor would I ever do such thing. How do I security? Shares, allow, oh, I just figured it out. Okay, now you can do it. Share your
Okay,
screen,
so-
show us what's up.
Okay, so let's, yeah, that's fine. Cool. Share. All right, can you see it?
Cool. Yeah, this is awesome.
I guess this is just my test, but yeah. So basically, I just uploaded it, and there's like a little marker, and you have all these different colors, and
Wait,
you can just.
where's the marker? Show us again.
Can you see it right here?
I can see your mouse. Oh, right there. Okay.
Yeah. So like it was right here. I clicked that. I think it's just add notes, and then you got all these different colors. I mean, they're not perfect, obviously, so we can work with what we got, but
Yeah, no, that's fine. It doesn't have to be true color.
yeah. Then you can
And when you save this, it'll save all this stuff.
yeah, you just got to press save as. So and like it's only on this paper. Like it's kind of cool. I didn't know about this.
That's so sweet. Thank you so
So-
much. And that's just through Microsoft Internet
Edge, yeah.
Explorer. Like it just shows up automatically, right?
Yep.
Killer. You're probably gonna want to use thinner lines. That green one you had was about the right thickness. Okay.
Oh yeah, I was just. I'm gonna. This is my test paper, so it's not even.
Okay.
Not even the real one.
So let me share my iPhone with you guys so I can show you how this is gonna work.
Stop share. So.
I'm gonna just kind of do mine on the paper because, well, that's a little more natural to me, I guess. Okay, hold on a sec. Share screen, iPhone. Let's hope this is going to work. Because of the difficulties of doing this over the internet, I normally have students do a whole bunch of atoms, but I think we're just going to try to do 4 spectra together, okay? So let me see if this even works here.
I'm attempting to write my name on the paper with this, so it looks
Use the
like a 5-year-old with
Why
crayons.
don't you just
so-
use the type tool? I noticed you had a type tool there.
Did I? I didn't see it.
Didn't you?
No, it says add notes, but that's.
Oh, I thought I saw something like a letter A. You could have a type tool. All right,
Oh,
fine.
that's just a highlighter.
Oh, okay. All right.
Yeah.
Shoot, my thing is acting funky wonky here. Let me see what the fudge is going on. Let me try that one more time. I might have to reboot my phone, which is extremely irritating. I knew if it worked earlier that it was going to give me trouble later. It's never as smooth as I want it. All right, you bastard. Let me start here. All right, at the top, why don't we write our names? And let's write AS1010 for section. Do you guys see where it says, I'll have to manually explain this, gas name here?
Yes.
The first element will be hydrogen. Unfortunately, hydrogen's contaminated, so it's gonna look kind of bad, but it's because I grabbed the wrong hydrogen tube when I was getting the supplies for this class.
Can we do like abbreviations for these if we're doing it on the computer?
Yeah,
Okay,
Sure.
because because it's just super hard to write on a mouse and keyboard.
That's fine. Hydrogen is H, helium is He.
Okay.
We're gonna do neon.
Is
I
that
want
number
to
2
do
or 3?
a light bulb, an incandescent. Hold on, when my thing loads, I'll show you guys for reals. There we go. Come on, Governor, let's get this going here. All right. So I have hydrogen, helium. We're going to do an incandescent bulb. And we will do the solar spectrum. That might actually be too much too, but let's see if we can get these done. Now, I'd like to point some things out. Do you guys see your chart here? The chart uses an old-fashioned unit called angstroms. Angstroms have the symbol of an A with a circle over it. And 1 angstrom is 1/10 of a nanometer. Or in other words, 1 nanometer is 10 angstroms. For instance, when we record hydrogen alpha, 656 nanometers, to convert that to angstroms, we just need to add a 0. 65, 60 angstroms. That's not too hard, right? The problem is that our spectroscope is going to put things. Oh, shit. Close that because I might need that for a lab later. Okay, so the way my spectroscope works is light enters into this tube here and there's a slit. It travels down and it bounces off this diffraction grating, and then it comes back up and it's scattered onto a spectrogram. Let's look through and let's see if I can see my spectrum there. I'm kind of holding this up. I'm going to sort of zoom in here. So you guys will notice that you can see 700 nanometers on the left, 600, 500, 400. So this spectrum here is going to be Roy G. Biv, but here on our page it's going to be Viv G. Yor. So we'll need to be careful and quantitative about it. Let's start with hydrogen. Can you guys hear me? And sort of, I want to make sure, sorry. I'm going to get myself in the background so you can kind of see what I'm up to. I'm going to get this lamp so I can get some background light in my spectroscope. Hold on, guys. It's pretty tricky to do this. Shit. Well, let's see if one of those worked. Okay. Do you guys see all those green and orange lines in the background? That's all contamination from air, okay? Air is contaminated my hydrogen spectrum. Now, if you guys can see the lines that we're looking for, do you see that red line there?
Yeah.
Notice that 600 is on the right, 700 is on the left, The big tick marks are 10 nanometers. The little tick marks are 5 nanometers. What would you say is the wavelength of the red emission line?
Five.
It's a little blurry because my phone sucks.
Is it
Oh,
low?
wow.
Would
Huh?
it be roughly 650?
Yeah. So on our page, that would be 6,500, right? So I'm going to take a red emission line for hydrogen. This is 620, 640. And I'm going to make a red emission line right at 6,500. Let's check out the blue one. Unfortunately, these look kind of bad compared to other ones I got.
That one was good. Yeah, do that one.
No, the numbers are real crappy.
Oh.
Okay. Let's try to get the blue one. This one's okay here. What would you say the wavelength of the blue emission line is?
$45?
No, 45 is, wait a minute. Do you mean the number 45? It's clearly between 400 and 500, right?
Yeah, so 485.
Oh, 485. Yeah, that's great. Sorry, Brandon. 485.
I'm super
I thought you
confused.
That's a blue line. That's 480, so we'll put it just past 4,800. Now, unfortunately, CCD cameras are really sucky, not very sensitive to violet. So also the air is contaminating my spectrum and making it really horrible to see the violet end of it. I think it's, do you guys see how there's a slight enhancement of the purple? 2 tick marks over there?
Yeah.
So I think that's the hydrogen gamma line. And that looks like it's at 410, 420, 430.
Yeah.
So we'll put the gamma line at 4,300. That's a violet crayon. And we'll go to 4,200, 4,400, and 4,300 is right in between. And so unfortunately, the air has contaminated that one. I have a deuterium bulb that doesn't contaminate quite as much, and deuterium is about the same. But you'll also notice, if you want to take special notice, this is the hydrogen gamma line. That's the hydrogen beta line. This is just for funsies.
Okay.
And this is the hydrogen alpha line. These are some of the most famous emission lines in all of astronomy. Okay, ooh, I should have turned that bulb off because they get hotter than holy hell. No Bernie. Just a second here. Here's a helium bulb. You guys ready for the next one?
Yeah. Do you want the hydrogen beta, hydrogen delta written on the page with it?
I mean, I thought that was a classy move. I didn't have you put the hydrogen delta line, just hydrogen alpha, hydrogen beta, and hydrogen
I just have to
beta.
copy that real quick.
Yeah, sure.
Um,
I usually don't make students do that, but I thought it would be kind of cool.
yeah, I just have to copy.
Teacher's version of cool, you know?
Yeah, all right, so
Okay. Let's try to check out. Obviously, this lab is way freaking cooler when you're doing it in person, right? But times being what they are, COVID and all that shit. Notice the overall color of helium is not the same as the hydrogen. That's pretty dope. Wow, that one came out good. Not bad, huh? All right. Let's see if any of these look good. Whew, that's brighter than hell. Wow. That yellow line is really popping. Oh, this one came out magically good. Look how nice that is. So we got a red line. What would you guys say the wavelength of the red line of helium is? What is that?
660.
659.
Wait a minute. Can you guys see my mouse at all? You probably can't see my mouse, can you?
Yeah, I can see your mouse. Yeah.
Oh, cool. This is 600, 610, 620, 630, 640, 650. That's 660. That's,
Oh, 669.
yeah, 669 is probably right. So we'll just go a little past 6,600. Hold on. So here's helium. 62, 64, and there's 66. We'll go a little bit past it. Notice it's not quite the same as hydrogen alpha. It's at a different wavelength and a different energy. Y'all mean? How about that golden? Hey, you know, I always have debates with students when we look at this line. The boys all think it's orange and the girls think it's yellow. I'm kind of torn. It's kind of a golden rod.
Yeah.
I'd say it's probably more yellow than orange, but I don't know if that means I'm a girl. Whatever. Okay, what's the wavelength?
Six or 585.
585 sounds good to me. So I'll put it just past 5,800. I'm going to split the difference and I'm going to blend yellow and gold just for artistic purposes. So here's 5,800. I'll go a little bit past there. Yellow doesn't show up good. So I'm going to do a kind of sweet blend with orange. What would be the name of a color that's halfway between yellow and orange? Goldenrod? Is that what we'd say? I don't know. All right, what else we got? A couple of teal lines, right? One's at 500, what's the other one at? Talk teal. Teal talk, what do you got?
490. One's at
490
500.
and 500. So we'll get those next. So 490 is halfway. This is 4,800. This is 4,900 here. I'm even going to make this one thin and that one darker, trying to show you the relative line strengths. Different emission lines have different strengths based on something called selection effects. Not every transition is equally likely. But that's shit that's way over your pay grade at this stage. Selection effects, man. Get with it. Okay. This one came out real nice. I see a violet, that almost looks like a doublet, doesn't it? A violet doublet, that's 445. And then a kind of indigo line at 470. So I'll get a sort of indigo for 470. That's here in between these two tick marks. And then there was a kind of violet-y, darker looking line. This is still kind of indigo at 445. Check out those nuanced shades of indigo, people. Okay, I think that's it, right? Oh, wow. They look more purple here. That's interesting. Very fun, very fun. Should we try neon? Get crazy?
Can you just go to the paper after for 1 second? I missed just one line.
Yeah, sure. Let me swap out my neon and then we'll do that. Sorry. Just a second. Can I? Let me take off the lock here.
All right, so hold on. Right there, then right. Blue, right. All right, I'm all set. Thanks.
Sure. All right. Let's do some more spectroscopy. Oh, the markers. Look at that neon, huh? Hella bright. Neon has a lot of lines, so we're gonna have to be smart about this. Hold on, something's funky here. All right. That third one came up pretty darn good. Wow, look at that. There's actually even green and blue lines in there, but they're fainter, it's harder to see. Okay. There's actually a real faint line, a faint red line up there at 790. Let's count them. I see a faint line at 790. I see 1, 2, 3, 4, 5 kind of clustered around 750 to 770. So we'll put 5 lines in for starters. So we'll go to neon.
Did you say 750? Do you mean 650?
Yep. Sorry, dude. That was a dumb move. So that's like a student move right there. I shouldn't have done that. 1, 2, 3, 4, 5, something like that. It doesn't have to be perfect. 600 is definitely orange. I'd say I've got like 1, 2, 3, 4, 5 in between 650 and 620. Put another 5 in there. We're just kind of doing it real fast.
You also forgot the one at 690.
Yeah.
Sorry.
Right. Now we're just kind of, neon has two. If we do the neon too precisely, we'll be here all day. So we're kind of winging it on neon a little bit. Now, how many orange lines would you say there are? Maybe 1, 2, 3, 4, 5, 6 or so.
Yeah, 6.
Kind of a lot of lines. Let's try to get some of them in orange. I'll put 3 on this side, 3 on the other side. And let's throw a few yellow lines in, maybe about 3, 690 to 680. I kind of messed up my numbers a little bit, but that's okay. We'll just throw in a couple yellows. That's sort of what the spectrum of neon looks like. Probably could have done that better, but it's the flavor of the feeling. Everyone got that? Okay. Let's try an incandescent bulb and see how that goes. I've got incandescent here. What type of spectrum will the incandescent bulb produce, students? What type of spectrum?
A rainbow.
Which is also known as? A continuous spectrum. Check this out here. Ooh, doggy. I want to move it off axis a bit. The color discrimination for the CCD camera is not as good as the human eye. Come on. Can you guys see how it's continuous, that there are no breaks?
Yeah, it kind of goes in and out sometimes. You can see it.
Okay. So this wasn't my best ever picture of a rainbow. Let's start here. So what we're going to do is we're going to try to be quantitative about this. Purple goes from 400, but by 450, it's starting to turn kind of indigo. I don't know if I really captured the nuance of the indigo anywhere here, but let's start. We're going to shade this continuously, okay? So I'm going to start with violet. So violet's going to start at like 400, and it's a smooth rainbow. By the time we get up to 440, we'll stop. Around 440 to 460, it gets indigo. It'd be nice if you had a sweet indigo pencil like the one I have. It's kind of a decent indigo. I'll even kind of change my indigo. I've got 2 indigo shades there because I'm crazy. And I'm even going to then transition into cyan or sky blue. That's only because I've got a sweet set of markers here where I can really transition from violet to indigo to cyan. I've got a couple of greens, so I'll do it right. I think I'll start with the dark. Really, it should be kind of a teal green, but I'm going to start with a forest green at 500. You guys will notice that the green starts around 500. It's kind of teal, and then it transitions to yellow green around 560 or so. So I can do green for a little while. Around 540, I'm going to kick my green into the kind of lighter green color. I'm trying to be pretty slick about this. After that, it starts to look yellow. Yellow is a very, very narrow range. Look at how narrow yellow is. It looks like, what would you guys say the wavelength range of yellow is?
Like 10 or 20, maybe?
Yeah, and it goes from, what is this? 550, 560, 575 to 585. It's pretty narrow. So from orange kind of goes to about 610 or so. So orange starts here, goes to about 610 or 620. And after that, it just starts looking hella red. I actually have two shades of red. I'm not sure which one I should do first. Which one of these? They almost look identical, don't they? Do they have names? No, this isn't crayons. I guess I'll do like the lighter red first. Then I'll do a sort of deep, deep red. Cool. Hold on. That's what my spectrum looks like. What do you guys think?
Can you just like hold it there for a minute?
Yep. I'm gonna do this so my hand doesn't shake.
Thank you.
Sure. Looks like a couple of people are still coloring, so I'll give you a sec. I've really got to do some grading. So what are we going to see when we look at the spectrum of the sun?
Wasn't it a lot of greens and blues and then like red?
Let's find out. Oh, shoot. Damn it. I hope I can get this back. Nuts. I didn't mean to do that. Come on, baby. Yes. All right. Now, we don't actually have to point this thing at the sun because the solar spectrum gets preserved in the scattered blue sky or in the scattered white light of the clouds. So let's see what we got going on out here. Got a pretty overcast sky. Ought to be perfect. That should preserve the spectrum of the sun quite nicely. Just a sec. I don't know what that giant blue line is. I'm trying to, I think that's contamination. Hold on. I think there's a bit of light that's leaking in the front. That's, oh, shit. That's what I want. What do we see, Brandon? Let's see if we can find the absorption lines. I was hoping to get that. Can you guys see that there's super, super faint lines there? Hey, Jordan, can we try it with your phone? Because you have, she's got the bloody iPhone X or 10. She's got an iPhone 10 and her, I've got the iPhone 5. That tells you where I'm at. So her camera is going to be way, way higher resolution. So are you connected to the Wi-Fi? Okay. So let's just, if we could see the absorption lines, I think it would be really, really worth it. Okay, so I'm going to go to share screen. And then what I need you to do is kind of swipe up, or whatever you do, you swipe down on your model. Shoot, sorry.
Screen mirroring?
Yeah, screen mirroring. And it should say Zoom. Click that. Okay. And now just go to your camera. Just your live camera. Okay, cool. So can you guys see this? Oh, it's screen sharing is paused. Why is it resume share? Are you guys seeing this? Here, can you go back to your... Let me stop the share. Just bear with me, guys. Hey, is anyone there? You're all black right now.
Is the Wi-Fi?
Hello? Does anyone hear me?
I don't think the Wi-Fi is working.
Oh shit.
Can I do it without the Wi-Fi?
No, you have to do it the Wi-Fi.